Hello, and welcome to another video presentation courtesy of the University of North Texas Physics Department with the aid of the Physics Demo Room. My name is Corey Nook, and today we're going to be talking about the conservation of linear momentum. Now, a lot of you might have seen something similar to the demo we're going to be working with today. We're working with an air table today to help illustrate the conservation of linear momentum. This is really similar to, like, say, an air hockey table that you might find at like some sporting areas such as like Dave & Buster's or Chuck E. Cheese or any arcade center that might have one of these. But we're actually going to start talking about what's really the physics going on here and how is this really actually not only fun at home, but also educational for us. So I want to point out just for initial purposes that I have this table in front of me, which on the end has a hose. All it is just going to be blowing air, and there's little holes on the top of here, and it's going to blow up, and it's going to create a frictionless surface or an air surface for us to see. But as you also notice that if my hand is here, you also see my hand up on the back of the board. This is to help visualize the overhead view of our little table. That way we can see it in more than one dimension, and that way you're not getting kind of a distorted view from looking at it at the side. So some of the things that we need to talk about, though, is the conservation of linear momentum. It states that if I have a bunch of objects moving with some velocity, that the collection of objects, that their momentum before any collision is going to be the same after any collision. Now remember that momentum is defined as the mass of an object times its velocity, not its speed, but its velocity, which means that we have to always consider the components of that velocity. So in reality, we should look at is that the component of the system of the momentum is equal to the final component of that same component of that momentum as well. So this means that the momentum of the system initially in the x direction has to equal the momentum finally of that system in the x direction, and the same in the y. So this is where some of these problems can get really difficult in a hurry, because let's say I take this puck, and if you notice that I have it down here on the corner, and now I move it that way, it all of a sudden travels in this trajectory, kind of like I'm doing with checkers. I'm almost making a 45-degree angle. Well, now this means that I'm not just moving in my x direction, I'm also moving in my y direction. And that way I'm going to be looking at it like so. So when I'm doing these problems like this, so let's say if I had this puck here, and it's just going around at just purely in the x direction, and this puck is going at a 45-degree angle, means that afterwards, the momentum still has to be going in a y direction, and it still has to have a net x direction. Now with this, I'm going to guess that both these pucks, that we're going to have some component going still north, and still some component going to the my right direction, or in this way, because if these were both put at the same speed, because this second puck is going at a 45-degree angle, the magnitude of the velocity is the same, but the component in the x direction is less. So that means that this puck is going to have a greater component, and it's going to transfer some of that momentum. That way the total momentum is going to be the same in that direction before the collision as it is after. So now we have a few different types of collisions. Now with these, most or less, these are going to be elastic collisions, which means that not only is the momentum conserved, but also the energy is conserved. This is very different than, let's say, if all of a sudden I put gum on the side of this puck, at which point these two came together and stuck. At which point, how is the system going to move? At that point, with the gum on the side, the energy is no longer conserved because it's an inelastic. If you ever have a question about which one is which, or having trouble remembering, just think of it like elasticity, like a rubber band. It likes to bounce off. It doesn't want to stay. It wants to keep moving. Whereas inelastic, you can almost think of like in the other object or with the other object. Kind of like if you have a train and a car, that train is going to go into the car and destroy it. Never a fun thing to see. So With this, we're able to kind of visualize, hopefully if I can get these down in terms of some relative speed, we can actually do some mapping if we really wanted to, of over some time of going, well, if I had this object moving here and I try to push this object, that way they hit at the same time, where should they go? So what we're going to do is we're going to try and actually turn on the airbag. Hopefully it won't be too loud. And we're going to try and notice that if I try to get these at about the same velocity, when they hit, where are they going to go? The other thing that's also kind of unique about this is that if we had enough objects, we can kind of describe what's called Brownian motion, which is just like random motion of particles as they kind of interact with the air. So hopefully you can at least see one of these pucks is starting to move. This guy's in a little bit interesting area. And this puck is starting to randomly move on its own. Now if I just give it a little bit of a touch, there are strings on the end to help it just from keeping flying off the edge. You can kind of tell we have this. So what I'm going to do is I'm going to try to see if I can get something started here, where I'm going to try to see if I can push these two at the same velocity, going in the same direction, and having them bounce off each other. Now you might say, well, Corey, why did those two all of a sudden go at an angle? Is because if you watched carefully, when they got to here, now their momentum, instead of purely being in the X, when they interacted, they didn't collide head on, they collided at an angle and transferred that to be going in the opposite direction. So this is where we have to be careful. Again, it's going off at an angle, perfectly hit, it went straight back at an angle. So this is where those collisions you can also apply to, let's say, a standard ball on top of a ball. If it doesn't hit perfectly exact, it won't go where it came from. So now I can go at the corners and I go back. And you can kind of hear that little bit of a sound. And that little bit of a sound is kind of partially not a purely elastic collision as well. Now I can try with bigger objects. Hopefully I can hit them easier. And we can see in both, at least the X direction and the Y direction, I can overall get them to go back and forth. So now let's say I move this one really slow, that one really fast. This one that was really moving really fast changed its momentum with it. It transferred it. So I'm moving that one's really slow, that one really fast. It changed or it switched its momentum, it transferred it. Moving slow, moving fast. So I'll move this one really slow. See how with that one, the momentum transfer went from one object purely into the other and made it go really fast. You'll see this a lot in pool, when someone will take a cue ball and they'll hit another one, and where the cue ball will actually stay and give all the momentum to the other ball that they're hitting. Well, thank you for attending this video presentation and have a wonderful day.